When we're integrating, we need to be able to recognise standard forms and use them immediately. There are also standard methods for integration, but for now we're going to concentrate on the standard forms of integration. And the first one we're going to have a look at is the integral of x to the n with respect to x. To do this, we take x to the power n plus 1. So we've added 1 to the index and then we divide by the new index. We must remember to add on a constant of integration, c. N can be any number, a whole number, a fraction, a decimal, except it cannot be minus 1. If it were minus 1, we'd have minus 1 plus 1 would be 0, and we're not allowed to divide by 0. So in this particular case, n does not equal minus 1. An extension to this would be ax plus b, where again a and b are just numbers, just constants, again raised to the power n. Ax plus b is very little different to x. So again we add 1 to the index and divide by the new index. But now, because we're multiplying our variable x by a, we've got to divide by it, because in essence we are reversing the process of differentiation. And again we must have plus a constant of integration c, and again we cannot have n being equal to negative 1. Next standard form is the integral of 1 over x. We saw this when we did differentiation, because we saw that the derivative of the log of x was 1 over x. So if we reverse that process, the integral of 1 over x must be the log of x. And we must include the constant of integration c. If we have 1 over ax plus b dx, and again a and b are constants, then what we must have is 1 over a, the log of ax plus b. And again, we must include a constant of integration. Let's just have a look at an example of this. The integral of 1 over 2 minus 3x dx. Here we can see that the a is negative 3, so that's going to be minus 1 over 3 log of the modulus of 2 minus 3x, plus, again, the constant of integration, c. Next standard form, the integral of e to the x with respect to x. We know that e to the x is its own derivative, so when we integrate it, we must get exactly the same form, e to the x again. What if we've got e to the mx dx? Again, thinking as integration as reversing differentiation, we need 1 over m, e to the mx, because if we were to differentiate e to the mx, we'd get m e to the mx, and we'd want the m's to cancel out. And again, plus c. Let's just have a look at an example of that, the integral of e to the 4x dx. And that will be 1/4 e to the 4x plus a constant of integration, c. We'll move on now and look at the trig functions and look at the standard integrals associated with those. So, the integral of cos x dx. The derivative of sine x is cos x. So if we reverse that, the integral of cos must be sine x, again plus a constant of integration. If we integrate cos nx dx, well, we know what happens when we differentiate sine nx. We get n sine nx. So when we do the integration, we're going to have the sine nx, but we've got to have 1 over n sine nx. And again, plus the constant of integration, c. What about doing sine, the integral of sine x? Again, we know that the derivative of cos is minus sine. So if we integrate sine, reversing the differentiation, it's got to be minus cos x plus c. And similarly, if we have sine nx dx, then it's got to be minus 1 over n cos nx plus c. What about tan? Integral of tan x dx. We know that the integral of tan we can change to be the integral of sine over cos dx. And now when we look, we can see that the top is the derivative of the bottom within a minus sign, because the derivative of cos is minus sine, and so we have minus the natural log of cos of x. When we're subtracting a log, we're dividing by what's inside. And if we divide by cosine, then that's the same as sec. And so we can show that this is the log of sec of x. And again, we must have plus a constant of integration, because these are indefinite integrals. There's another one that we can take, and that is sec squared x dx. When we did the differentiation of tangent, we saw that when you differentiate at tan, you got sec squared. And so if we reverse that, the integral of sec squared must be tan x, plus a constant of integration, c. And if we've got sec squared nx dx, then again, this must be 1 over n tan of nx plus c. Now we're going to look at some rather more complicated ones, but they are worthwhile remembering because they can save an awful lot of work if you can identify them. These are connected with the inverse trig functions. So we have the integral of 1 over the square root of 1 minus x squared with respect to x. With the differentiation of the inverse trig function, we saw that when we differentiated sine to the minus 1 of x, we got this. And so if we reverse that, sine to the minus 1 of x must be the answer to the integral, because integration reverses differentiation. Similarly, we have something that looks very much the same, a squared minus x squared dx, instead of 1 minus x squared, then the integral is sine to the minus 1 x over a plus c. Let's have a look at some examples using this result, because sometimes we have to work a little bit hard at this side. Let's take a straightforward one, square root of 4 minus x squared. Now we can identify the 4 with the a squared, so it's fairly clear that a must be equal to 2. So we end up with sine to the minus 1 of x over 2 plus c, the constant of integration. But what if it doesn't quite look like that? What if we've got something here in front of the x squared? So we take the integral of 1 over the square root of 4 minus 9x squared dx. Here we can identify the a as being 2, but we've got 9 here. We really do need that just to be an x squared. So what we're going to do is take the 9 out through the square root, and as it comes through the square root, we will have to square root it, which is going to leave it as a 3. And so we're going to come to this, the integral of 1 over 3, 1 over the square root of 4 over 9 minus x squared with respect to x. Now, this does look like one that we've done before. We can keep the 1 over 3, that's fine. And now we need sine to the minus 1 of x over a. And what is a this time? Well, a is 2 over 3, because a squared is 4 over 9. So that's x over 2 over 3 plus c. Dividing by a fraction, we know how to do that. We invert the fraction and multiply, which gives us sine to the minus 1 of 3x over 2 plus c. So we see we can do these quite easily by trying to get that coefficient of x to be 1 and not the number that's actually there. The other hyperbolic function that we met was tan to the minus 1. And the derivative of tan to the minus 1 was this function, 1 over 1 plus x squared. So if we want to integrate 1 over 1 plus x squared, the answer must be tan to the minus 1 of x plus c. And in the same way as we had an a squared in there, let's put one in now in this one. dx, what do we get? This one, standard result, 1 over a, tan to the minus 1 x over a, plus a constant of integration, c. Let's take an example. 1 over 9 plus x squared dx. 9 and a squared are the same, so a must be equal to 3. So that gives us 1 over 3 tan to the minus 1 x over 3 plus c. Same question as we had before. What if it's not a 1 there? What if there's a number in there? Well, again, let's have a look. Let's take the integral of 1 over 25 plus 16x squared dx. What do? We try to get a 1 there, which means we take the 16 out. So we'll have 1 over 16 integral of 1 over 25 over 16 plus x squared dx. The 1 over 16 can stay as it is. This is now a squared, so a must be 5 over 4. So we want 1 over a, 1 over 5 over 4, tan to the minus 1 of x over a. So x over 5 over 4 plus the constant of integration. Now we need to tidy that up a little bit. 1 over 16 times 1 over 5 over 4 is 4 over 5. Tan to the minus 1 of 4x over 5 plus the constant of integration c. And we can make a simplification here by dividing by 4, giving us 1/20. 4 and 4 cancel, and 4 times 5 is 20. Tan to the minus 1, 4x over 5, plus that ever-present constant of integration, c. Now, those are all the standard forms. Once you've seen them and used them, they're well worth learning. Learning because you can recognise them and you can use them straight away, and you don't have to worry about how to do certain forms of integration, because they're just there. They're just part of what you do all the time. But learning them is very important.